All right, welcome. Today, we're going to dive into a really powerful extension of a tool you probably already know, binomial expansion. We're going to go way beyond the simple whole number powers you're used to and see what happens when we throw fractions or even negative numbers into the mix. It's a pretty small change, but trust me, it unlocks a whole new mathematical universe.
So you're probably pretty comfortable expanding something like 1 plus x cubed, right? You get a nice, clean answer, a few terms, and you're done. But what happens when that power isn't so friendly? What if it's, say, -3, or a fraction, like the power of 1/2 you'd use for a square root? Suddenly, that neat, tidy answer just disappears. The old rules just don't work anymore. And that means we need a new, much more powerful formula.
And that's where this comes in, the general binomial theorem. This one formula is the master key. It unlocks expansions for, well, literally any real power you can think of. Negative, fractional, you name it, it can handle it.
Okay, and this is where things get really different from what you might be used to. There are two huge changes you absolutely have to keep in mind. First off, when our power n isn't a nice positive whole number, the expansion doesn't stop. It becomes an infinite series. It just keeps on going, forever. Second, and listen, this is the most important rule of the whole explainer. The formula only works if the absolute value of x is less than 1. If you forget that, the whole thing just falls apart.
So, here it is, the formula itself. Let's just walk through the pattern together because once you see it, it makes perfect sense. It always starts with 1. The next term is just nx, simple enough. Now for the third term, you start to see the pattern emerge. We take n, multiply it by n minus 1, divide by 2 factorial, and then multiply by x squared. So what about the next term? Well, you can probably guess it. We multiply by 1 less again, so we've got n minus 1, n minus 2, we divide by 3 factorial this time, and we multiply by x cubed. It's this really beautiful, predictable pattern that just keeps repeating on and on and on.
Okay, theory is great and all, but the best way to really get this is to see it in action, right? So let's put this formula to work with a couple of examples.
First up, let's tackle an expression with a negative power. Our mission is to find the first 4 terms for the expansion of 1 minus 3x to the power of -2.
You know, the process here is always going to be the same. First, you just identify your pieces. So in this case, our power n is -2, and the thing taking the place of x in our formula is actually -3x. You got to take the whole thing. Then we just plug those values into the formula we just looked at. Now a little pro tip, the key here is to use brackets around that -3x. Seriously, it's a simple habit that will save you from so many headaches when you're squaring or cubing a negative term. After that, it's really just a matter of simplifying carefully to get our final result.
All right, ready to level up a little? What if the term with x is a bit more complex? So in this example, we're expanding 1 plus 2x squared all to the power of -4. The logic, though, is exactly the same. Our n is -4, and this time the entire 2x squared term is what we're going to substitute for x in our general formula.
So the process is identical, but you really have to be extra careful here. When we substitute 2x squared, you have to remember to apply that outside power to both the 2 and the x squared. It's so easy to forget. Like you can see in that x to the 4th term, we square the whole 2x squared to get 4x to the 4th, not just 2x to the 4th. This is a super common place to make a mistake, so again, always use those brackets.
Okay, so we've used the formula twice, and it worked out great. But remember that super critical rule we mentioned at the beginning, the one about how these infinite expansions don't always work? Well, let's dive into exactly what that means. Because this rule, it's completely non-negotiable. Just think about it for a second. If you're adding an infinite number of things together, how can you possibly get a real answer? The only way is if those things you're adding get smaller and smaller and smaller, basically heading towards 0. I mean, if the terms got bigger, the sum would just explode and shoot off to infinity, right? That's not a useful approximation at all. This whole idea is called convergence. And this leads us to a really simple but incredibly powerful rule. Whatever that term is in the u position of our 1 plus u n formula, its modulus, which is really just a fancy way of saying its absolute value, or its size without any negative sign, that has to be less than 1. That is the magic condition. If that's true, every term in our series will get smaller than the last, and the whole thing will settle on a real, actual number.
So let's apply this to our first example, 1 minus 3x quantity -2. Remember that the term in the u position was -3x. So we just set the modulus of -3x to be less than 1. The modulus, remember, just eats the negative sign, so that gives us modulus of 3x is less than 1.
A quick division by 3, and boom, we find that our expansion is only valid, only a good approximation, for values of x between -1/3 and +1/3. Okay, so now that we've got the formula down and we understand the all-important rule for validity, it's time to put it all into practice. Let's tackle a few problems from exercise 7C, because this is where you really start to build your skills.
All right, let's look at a few of these. Part A is pretty straightforward. N is -2, our u term is just x, so the validity is simple. X is less than 1. Easy. Now, part E has a square root. But don't forget, a square root is just a power of 1/2. So here, n is 1/2 and u is 2x. You apply the formula, and for the validity, you set 2x is less than 1, which of course simplifies to x is less than 1/2. Okay, now part H looks a bit tricky. It's a two-stepper. You've got to rewrite it first as 1 minus 3x times 1 plus 2x minus 3. Then you expand the 1 plus 2x minus 3 part using our new method and multiply that whole infinite series by 1 minus 3x, and then just collect the terms to get the final answer. Now, which part determines the validity? It's always the part you're expanding, so it's still based on that I2x is less than 1, which means Ix is less than 1/2.
Ooh, this is a great question. It's one of those that really tests if you understand the rules. At first glance, 3x minus 1 to the -2, well, it doesn't look like 1 plus u to the n at all, does it? So the big question is, can we even use our formula here? And the answer is yes. We just have to be a little clever with our algebra. The trick is to manipulate the expression until it fits the form we need. So what if we factor out a -1 from inside that bracket? We'd get -1 times 1 minus 3x. Now, when we apply that power of -2 to both parts, something cool happens. -1 to the power of 2 just becomes +1, and we're left with 1 minus 3x to the -2, which is exactly the form we need. Pretty neat, right? Okay, let's take a look at a classic exam-style problem. These are the kind of questions that have multiple parts and force you to combine what you know about binomial expansion with other algebra skills, like solving equations. So here's the setup. We're given an expansion, and we're told the coefficient of the x² term in this expansion is 90. So our first job is to use that piece of information to figure out the value of k. Then, once we've got k, we can use it to find other things about the expansion.
Now for part 1. The smart move is realizing you don't need the whole expansion. Not at all. We just need the general form for the x² term. So we plug in our values. N is -4, and our u is kx. That gives us the expression for the x² term. And since we know its coefficient is 90, we can set our coefficient expression 10k² equal to 90 and just solve it. The question says k is positive, so that means k has to be 3.
Awesome. So now that we know k equals 3, our u term is actually 3x. We're just going to follow the exact same process, but this time for the x³ term. We grab the general form for the x³ term from our formula, we plug in n equals -4 and u equals 3x, and then we just carefully simplify to find that final coefficient, and it turns out to be -540.
Okay, so after all of that, what are the absolute must-know takeaways from this? If you can walk away remembering these next 3 things, you'll be in fantastic shape.
First, get that general formula down. Really know the pattern. Second, always remember that for fractional or negative powers, you're dealing with an infinite series. And third, and honestly, this is the most critical point of all, you must check the condition of validity. This series only works, it only gives you a real answer when the modulus of your x term is less than 1. Don't forget it.
And that leaves us with a final thought to chew on. This whole process, it's all about making approximations. Since we can't possibly write out an infinite number of terms, we have to cut it off somewhere. So, how do we decide when our approximation is good enough? When is it close enough to the real answer? That's a really fascinating question in applied math. Thanks so much for watching.